All right, now we want to talk a little bit more about the stress-strain data that we obtained from our uniaxial tension test, right? And so we want to accomplish our final learning objective to determine some basic engineering properties using the stress-strain test data that we have performed and obtained from our experiment. All right, so we're going to dive here into our notes and get down a few more of these properties that might be of interest to us from our stress-strain curve. All right, so hopefully we remember what the stress-strain curve looked like. Stress is on the vertical axis and strain is on the horizontal axis. Remember, anytime we say stress versus strain, it's always y versus x. Now, initially we have the linear elastic region, and so this is a straight line up to some point where we start to experience permanent deflection. And I want to highlight just this beginning portion of our curve. So this is going to be up through the linear elastic region. Then we have kind of a bumpity bump thing, and we enter the yield plateau. And so I'm just focusing on that very beginning part of the stress-strain curve. In the linear elastic region, remember, stress is directly proportional to strain using Young's modulus, or the modulus of elasticity, capital E. So that is our first term I want to define. The modulus of elasticity is the slope or stiffness of the material in the elastic range, in the linear elastic range in particular. All right, so this linear behavior continues until we reach yielding, and we're going to say it continues until it reaches a particular spot that we call the proportional limit. So the proportional limit is going to be this little dot that I drew in here, and it's basically the end of the elastic range. So when we talk about elastic behavior, we talk about like a rubber band. It can be stretched and then it can return to its original shape. Once we enter the plastic range, we can no longer return to the original shape. We have permanent deformation. So the proportional limit is what we say is the end of the linear elastic range. So it's the end of the stress being proportional to the strain, because now the strain is rapidly increasing, but our stress is remaining roughly constant here in the yield plateau. I've drawn kind of the blue initially when we have a fresh material. Takes a little bit of extra force to start the yield plateau, and then there's a little bit of a dip, and then it starts to steady out. So we call this like the upper yield point and the lower yield point, and then the dynamic yield point. These are all terms that if you end up taking my steel design course, we'll take a little bit more in detail look at this behavior particularly for steel material. Now I want to talk about the yield stress. So from our previous curve, we had the yield stress identified. The yield stress is the variable capital F sub y. So Fy, this is the stress at which the material begins to deform plastically. So we have elastic behavior and we have plastic behavior. So plastic deformation is permanent deformation. Now, a lot of times we can look at the graph of the data and we should be able to pretty much see where the yield stress is, especially for like a mild steel or like the grade 50 steel that we had in our test. But other times it's very difficult to figure out where the yield stress is, especially for things that have a small yield plateau, for metals that have a small yield plateau and immediately begin to strain harden. We still need to characterize the yield stress so that we can design for engineering. And so how do we do that if the yield plateau is not obvious? We do it by what's called the 0.2% offset method. So what we do is we come into 0.2%, which is 0.002, and we find that point on our strain. Then we draw a line that is parallel to the linear elastic range. So that is a line with a slope of E. We draw that line until it intersects our test data. So you see I put an X where it intersected the yield plateau. Once we find where it intersects, we then can track that data point back to the y-axis, and that's how we officially determine what the yield stress is. So I'll talk about this more because we're going to run in our lab later on this week, we're going to run an actual test on a couple different materials. And so I'll be having you plot this data, and you'll be needing to use the 0.2% offset method to find the yield stress, because as you'll see in some of our samples for some of our materials, it won't be obvious where the yield stress is. Lastly, we want to define the ultimate tensile stress. This is the highest stress the material reaches before failure, and we say that this is F sub U, and we labeled this on our previous diagram for the stress-strain curve. Now, I don't really like to say before failure, so I'm going to cross this out. I like to say it's the highest stress the material reaches before fracture. Okay, and why do I want to make this distinction? Well, as engineers, a lot of times we don't want to allow yielding to occur in our buildings or structures or any kind of our parts. So sometimes, as engineers, we will decide that yielding is our failure. So I don't really like to say it's the highest stress before failure. It's the highest stress before fracture. Fracture being the ultimate separation in the material, whereas failure is something as engineers we can decide what we constitute as failure. So I want you to take a moment and think, as an engineer, when would it be unacceptable for you to have a part that stretches and permanently deforms? And then think about, in other cases, when would you allow that to happen, and why might that be useful to you? So go ahead and take a few seconds to think about it. You can go ahead and pause the video and then resume it once you have an answer. Hopefully you came up with some creative ideas as to when yielding might be an acceptable design condition. There's many plausible scenarios out there. I'm sure you can look on the internet and find some other things particular to your area of interest for engineering. For me, I'm in structures, and so one point when we definitely allow for yielding to happen is when we design structures for extreme conditions like blast or earthquakes. When we do that, we design to allow yielding to happen in our members. And we do that because yielding takes energy. And if you think about an earthquake maybe as it is applying the energy to a building, if we allow the materials in that building to yield, it will dissipate some of the energy from the earthquake, almost like absorbing the energy from the earthquake and then keeping the building in use, because remember, even though it's yielded, it hasn't physically separated. So yielding still means the building is safe. People can escape the building and get to safety. But then ultimately, even after the earthquake is done, we're probably going to have to retrofit that building and make some fixes, maybe change out some of the members or some of the connections that have yielded, because permanent damage will have occurred. So we'll accept permanent damage to prevent physical separation and catastrophic failure, and which would be more of a life safety concern. All right, so that's just one example. I'm sure you can find examples from your area of expertise. For instance, mechanical engineers, right? When you design cars are designed to crumple in accidents because all of that yielding and everything will take up some of the energy from the accident and will prevent all that energy from being transferred to the person inside the vehicle. So that's another example of why we would allow yielding but not fracture. I hope you enjoyed this video, and I look forward to taking you through an example of calculating stress-strain data and some of the properties in our next video.